So here we're designing an aircraft that just has wings and a fuselage. So we still have ailerons for roll control, and we're going to talk about trimming the aircraft in pitch and checking out its pitch stability. So let's say that we're designing this aircraft so that the fuselage points directly into the oncoming airflow at a certain speed. That's our design requirement. So let's say we know the weight of the whole aircraft, so we know the wings have to lift the same as the weight at that speed. So we're going to know that the angle of attack on the wing is equal to the angle of incidence based on our design requirement for it flying into the oncoming airflow. So to get the wings to lift the right amount, we can either increase their area, like increase the chord length or the span, or we can change the angle of incidence until we have the lift equals the weight. So we know that those forces balance at that speed, and we're going to have to check if the torques balance about the CG. So we know that our angle of attack on the airfoil is 3 degrees by our definition. So let's take a look at where the center of pressure is for the Epler 420 airfoil here. At 3 degrees, it's at 40.8% chord. So if we go into our lift and weight, we'll change this to 0.408. And if we look, the lift right here is directly through the CG. Our sensor here is, the CG is at 10.59, and the lift is right through there. So this aircraft could theoretically fly at that speed, at that angle of attack, directly into the oncoming wind, and those forces would balance. But let's investigate stability. So let's say either a passenger in the aircraft gets up and walks towards the back, so the CG moves, or let's consider a gust of wind coming from below that temporarily increases the angle of attack on the wings, just a bump of air. So we can take a look at what happens. Let's just say that the whole aircraft experiences a greater angle of attack of, let's say, 5 degrees. So now if we look from here, the aircraft is flying into the oncoming airflow like this, and we have an angle of attack on the wing of 3 plus 5. So that's 8. So if we take a look at 8 degrees, the center of pressure is at 36.4. So it's moving forwards. So it was at 40.8. Now it's moved to 36.4. So it's slowly moving towards the leading edge of the wing. So 36.4, if we go in here, change this to 0.364, and take a look at it again. So now we can see that the CG hasn't moved anywhere, but the lift is in front of it a little bit, so there's a torque about the CG, a pitching moment to want to pitch the aircraft up even more. So that momentary gust of air caused a pitching moment to want to pitch up the aircraft. Even after the air is gone, let's see what happens, because if we're now pitching up, let's say another couple of degrees, let's go in here and change this to 7. So now our total angle of attack is 10. If we go check at 10, we moved even farther forward to 35% chord. So that torque is only going to increase. So I move forwards even farther. So it's going to want to pitch up even more. And on top of that, the lift value is getting higher too because of the increased angle of attack. So you can see that this is sort of a feedback system where initially we were balancing our forces, balancing our torques, but as soon as a little disruption came in, our aircraft wanted to pitch up more, and then the center of pressure moves forwards, wants to pitch up even more, the center of pressure continues moving forwards, and it really wants to pitch up until this runs away and your aircraft can stall.